Okay, for the first part, we're going to be looking at finding limits numerically, and numerically means that we're looking at the table, which we could do by plugging in the numbers by hand, but because that becomes very difficult to do, we're going to use our calculators to help us. Plus, we can use our calculator on the whole exam, so we want to do that here. So this is the informal definition of a limit, although it sounds terribly formal whenever you read it. So I promise you there's a much worse definition of a limit that is in our calculus book with epsilons and deltas and all kinds of crazy stuff. But this is the main understanding that we need to have. So if there is a number L such that the value of f of x gets closer and closer to L, as x gets closer and closer to a number a, then L is called the limit of f as x approaches a. Okay? So here's what that means. Our x values, as it gets closer and closer and closer and closer and closer to a number, maybe like 3, right? As x gets closer and closer and closer to 3, so it could be 2, and then it could be 2.5, and then 2.9, and 2.99, and 2.999. Have you ever heard a teacher talk about, like, let's say that I want to walk to the back wall, right? If I want to walk to the back wall, I would start, and in the first second, I would walk half of the way there, right? So I'd walk halfway there, right? And then, if I walk half of the way now, there's my second trip, right? And then I would go half of the way, right? And then I'd go half again, and then I'd go half, and if I could keep going halfway, all the way to the wall, would I ever get to the wall? I mean, in reality, I'm right there at the wall, right? It doesn't make sense to go past the point, but technically, I would never, ever, ever actually get to the wall. So you probably heard a teacher do something sort of like that whenever you start studying decimals. So like you do, 2.9 and then 2.99 and 2.9999, and you're almost to 3, but you're not actually to 3. So that's what's happening here. Our number's getting closer and closer and closer to a number, and we're seeing what happens to our y values. The f of x here, that's your y values that you're looking at. And if it gets closer and closer and closer to a number, you have a limit there. If it doesn't, if it gets bigger and bigger and bigger or smaller and smaller and smaller, then we say the limit does not exist. So let's look at some examples of actually no, there's a little more notation I need to give you. So we can look at one-sided limits. So that example I just gave you, where I started at 2 and I had 2.5 and 2.9 and 2.99 and 2.999, that was what we call a left-sided limit because I was approaching 3 from the lower values, right? So that is the limit as x approaches a from the left. And if I wanted to approach a from the other direction, then I would start with approach 3 from the other direction. I'd start at 4, and then maybe 3.5, and 3.1, and 3.01, and 3.001. So you can approach 3 from either side of 3, right, above or below. So whenever we do this, we're going to see the limit of f of x as x approaches a, and then you'll see a plus sign behind it. Not in front of it, so if it was in front, it would just be the sign of that number. But it's going to be behind the number. What this means is that this is the limit as x approaches a from the right, or from the higher numbers. And then you might also see a limit of f of x as x approaches some number a here, and you have a minus sign behind it. It's not in front of it, just telling us like it's negative a. It's behind the number. And that is our limit as x approaches a from the left. So, in order for just limit as x approaches a to exist. So just for the limit from both sides to exist, the limit from the left and the limit from the right have to be the same. Okay? So let me just give you this next example. I'm going to graph this next example because I think it helps to see what you have there. So your equation is y equals x plus 3 over x plus 3 over x squared plus 4x plus 3. So whenever we look at this graph, I'm going to, not x, yeah, and x equals 3. So right here, what we're looking at as x approaches negative 1, we're looking at getting closer and closer to negative 1, either from the left or from the right. It doesn't look like it's going to be the same value there, right? Here, from the left and from the right, it looks like it is the same value. So let's look at how we can tell that without looking at the graph, just looking at this numerically. So what we're going to do is we're going to use our calculator, and we're going to put that equation in. Also, actually, I'm going to use the calculator, and I'm also going to use Desmos, because in your homework tonight, if you don't have a graphing calculator, you could use Desmos, and he'll do the same thing for you. So let's do the calculator first, because that's what you'll have to use in class and on your test. So for the function, we're going to go back to function mode, and let's go to y equals and type in our equation. We've got x plus 3 over x squared plus 4x plus 3. And we're going to go to the table. But the table is not incredibly helpful when you're trying to get closer and closer and closer to a given number. So, like you'll notice here at negative 1 and negative 3, we have errors. That's usually where they ask you about the limit, because anywhere else that limit is just the number that you have. We'll see that a little bit later. But anywhere else, the limit is not very interesting. They usually ask you about the limit at these places where you have errors in your calculator. So I can't really tell by this what is happening close to the negative 1 or close to the negative 3. So a trick that you can use in your calculator that makes this go the quickest, if you go back to table set, so if you do second window, all right, and I want you to go down here where it says independent and go over and make it ask. Okay, so go to table set, which is second window, and go down to independent and tell it ask. Let's go to your what? Oh, you closed the parentheses here, but you never opened it right there. So put that picture. Okay. So now when you go to your table, it looks like it is empty. And you think, oh no, I have messed up. But now, if we're trying to approach, right here we're finding the limit as x approaches negative 3, and that minus behind the negative 3 tells us from the left. So from the lower number. So we would be starting at negative 4, negative 3.5, negative 3.1, and so on. So if I do that, if I type in negative 4, I get negative 0.3 repeating. And then I can type in negative 3.5. So you can type in whatever number you want. You don't have to go by the set. Like you don't have to go change what is going up by each time. So this time I get negative 0.4. And then I'll try negative 3.1, which is negative 0.3. 0.4762 and negative 3.01. I get negative 0.4975. Negative 3.001. I get negative 0.4998. Negative 3.0001. No, this gives me negative 0.5, but sometimes it looks like it actually gets to the number. But if I go over and highlight negative 0.5, if you look at the bottom there, if you don't actually have negative 0.5, the calculator's just having to round it because it doesn't have enough space to put that whole decimal in that little table. So it's not actually to negative 0.5, but it's getting really close to negative 0.5. So looking at this evidence, what would you say it appears that this approaches? It looks like it is probably negative 0.5. Now the thing about finding your limits numerically is that they never give you a conclusive answer. You cannot, like, this is not proof that that this is actually true. It is just a really good guess that this is true. And it is actually the answer for this one, but sometimes some problems are harder than others. Sometimes you might have to actually get a little closer to the value to be able to see. So this looks like we've got negative 0.5. Now we need to go back and we need to approach from the right. So that means we need to start with the higher values and get closer and closer to negative 3 from the higher values. So now we would type in like negative 2, and that gives me negative 3.5 and negative 2.5. And I get, oh, I'm sorry, that does not give me negative 3.5. I was looking at the wrong thing. You should get negative 1. Yeah. You type in negative 2, you should get negative 1. I was looking at the next line, I think. And negative 2.5, you should get negative 0.6 repeating. And then negative 2.9, we get, look, oh, no, I didn't type in the right thing. Negative 2.9, we get negative 0.5262, or 63. And then when we type in negative 2.99, negative 0.5025, and negative 2.999. I get, and you may become convinced of what it's approaching long before you actually finish this table that I have set for you, and that is fine. All right, let's see. Negative 2.9999. And it actually makes it to negative 3 and negative 0.5 here, but if you go up and highlight either of those, it's not actually, it's just the calculators ran out of room. This is really 0.500025. So we're not quite to negative 0.5, but it looks like we're getting closer and closer and closer to negative 0.5, right? So I would say, based on this information, my best guess would be that the limit as x approaches 3 from the left is negative 0.5. Or from the right, sorry. So since I got the same number for both of these, from the left side we approach negative 0.5, and from the right side we approach negative 0.5, then that tells me that the limit as x approaches, this should have a negative right here with it, sorry about that. As limit as f of x, limit of f of x as x approaches negative 3, that equals negative 0.5. If those two did not match, if one of them was negative 0.5 and one of them was positive 0.5, then you would say that the limit does not exist. Okay, it's got to be the same number for that to happen. Okay, so questions on this part? All right. Okay, for this one, we're still using the same equation. This time I want to show you how to use Desmos, just in case you need to use it for your homework. So I've got this equation here. This time we want to look at -1, because -1 was the other place where we had problems. So we don't want the calculator, we want Desmos. Okay. So to do this on Desmos, and actually that should have been a -3 right there. If you look at the graph, like at -3, it does not look like there is a hole in the graph, right? Because 2.99999 is going to look like it's at 3 whenever you graph it. So it doesn't look like there's a hole in the graph, but there is. We just can't see it whenever it's graphed. And so as you approach from the left or from the right, both of those have values of -0.5. I think something different is probably going to happen over here at -1, just based on what the graph looks like. So to do this on Desmos, you're going to add a table, and it'll have an x1 and a y1, and over here for y1, you are going to type this equation, and maybe it'll let me copy and paste, but I think we have to put a little 1 behind all of our x's. Oh, come on, I got this to work the other day. We might have to do y1 equals. Oh, I got it to work yesterday. Why is it not working now? Let me try typing it in. Okay, so okay, divide by I'm not sure what I was doing wrong earlier, but now it's working. So you type in the equation, but you got to put a x1 instead of just the x, and let's see if we can make this a little bit bigger so it'll show. So if I want to approach -1 from the, let's see what's on your notes first there, from the left, so -2, -1.5, -1.1, -1.01, getting closer and closer and closer from to -1 from the lower values, then in Desmos I'm just going to type those numbers in, so -2, -1.5, -1.1, -1.01, -1.01, -1.001, and you can see what's happening to our numbers. They're getting smaller and smaller, and they look bigger and bigger and bigger and bigger, but technically they're smaller and smaller and smaller and smaller, right? Because of their negative numbers. So, so is this approaching a single number? It is not. It is going to negative infinity is what's happening here. So this limit right here, and I'm not going to fill all of those in since we did this on Desmos, that limit is negative infinity. You also could say that the limit does not exist because infinity can't be a limit, right? It can't have a speed limit of infinity. Wouldn't make any sense. So from the left side, we approach negative infinity. If you look at the graph, that kind of makes sense, because if you're tracing this graph right here, as you get closer and closer and closer to -1, you just go down forever, right? So it never actually touches that line, so that kind of makes sense. So then, if we want to check this from the right, we would start probably at 0, and then maybe like 0.5, and then we start at 0, then we need -0.5, -0.9, -0.99, -0.999, -0.9999, and so it's really the same thing's happening, except for they're all positive now, and you can see on the graph it's getting higher and higher and higher and higher and higher. So our limit as x approaches -1 from the right would be positive infinity. Now, our limit from the left was negative infinity. Our limit from the right was positive infinity, which both technically do not exist. But they're not the same, right? One's positive, one's negative. So for the limit as x approaches negative 1, and there's no plus sign or minus sign behind it, so that means from both sides, they don't match. So you would have to say does not exist. A lot of kids like to write DNE. That is okay with me, but just make sure you know it means does not exist. Because on the final exam and on my test, it's going to say does not exist. Don't make it like an acronym that we all use so much we don't know what it stands for anymore, like NASA or ACT or things like that all stand for something, but I really don't know what. Sure, we can look at it. Okay, questions? Okay, so I'm going to let you guys work on a few of these real quick. We may not take the whole time, but I want you to put these into your calculator. And a lot of, like, some of these are going to be kind of crazy. Like, some of these are ones we could, the first one that I showed you, we're going to learn how to solve that one algebraically tomorrow. But things like number 2 and number 3, we're never going to learn how to solve algebraically. So if you were to see something like this on your exam, you would want to use your calculator this way to look at it. So go ahead and try these in your calculator, and notice x is approaching different numbers for these different things. So it probably usually gives you an error if you just plug in that number. But you would, like for 0, you would need to approach from the left, which would be like negative 1, negative 0.5, negative 0.1, negative 0.01, and so on. And then also approach from the left to see if it's the same. Yeah, it looks like for number 2, it looks continuous. Let me graph it on Desmos for number 2 just so you can see how crazy it is. Alright, so it looks like this. Let me get rid of this other stuff. It looks like this, but like, well, you can't see it, but it looks continuous, but it's going to give you an error if you actually type the number in. Looking at the graph, can you tell what it's going to be? It'll exist. Yeah, on your calculator, it's because your Y's are taller than mine are here. So, but for right now, let's just work on the table because the next thing we're going to do is the graph. So, let's finish this one together. So, I'm going to go delete all these out. Okay, if I want to approach 0 from the right, from the higher numbers, what number could I start with? 1 or 2 or whatever you want, but 1. And then what's a number closer to 0? 0.75. 0.5. 0.25. 0.1. 0.01. 0.001. And so the same thing's happening here. Don't pay attention to these numbers. Look at those. That scientific notation. Those negative exponents are getting bigger and bigger and bigger, which means the number is almost there. And if you're not sure, move your. Oh no, never mind. They're all scientific notation. It doesn't like giving those, but so you have to know about the scientific notation. But those numbers are getting teeny, 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 tiny, which means they're almost 0. Like whenever I was walking to that wall, whenever I was trying to go half the distance, eventually I got close enough, I was basically at the wall, right? If I needed to touch the wall, I could easily touch the wall. So we're getting closer and closer and closer to that teeny tiny number. We're basically 0, so we would say 0. So what we just found there is that the limit as x approaches 0 from the right of 1 minus cosine x over x was 0. And since those both match, what's the limit from both sides? It's 0. So that original question would be 0. Yes? Yeah, on that first one we did, it was negative 0.5. Right? So, on that first one that we did, we got negative 0.5, even though the limit that we were finding was approaching negative 3. So, it's just sort of a coincidence that it matches here, but it's not always that number. You want to do the next one together? Okay, let's do the next one together. Okay, let's type it in. I'm going to do this, but type it in on your calculator also because I want to make sure you know how to get everything typed in right. So you do natural log of x divided by x. Actually, we need parentheses around the denominator, x minus 1. Okay, so make sure you've got that typed in correctly. We'll go to our table. And I'm gonna go ahead and delete everything out. If you type in 1, you're gonna get an error. Now, if you ever type in that number and it gives you a number, then that's the limit. If that's the case, but they usually give you the one where there's an error. So, because then you have to figure out what it approaches. So, yes. Just go up to the top and hit delete. You can't hit clear. Clear doesn't work. Just hit delete. Is it working for you? Let's see. Oh, you have not changed. Go to second window. And then right here for independent, go down there and change to app. And then go back to the table and it will work. There you go. It's got to be on app for that to work. Okay? All right, questions? All right, so if I'm looking for the limit as x approaches 1 from the left of natural log of x over x minus 1. Okay, from the left. So I'm coming from the negative side. What number should I start at if I'm getting closer and closer and closer to 1? I could use a negative 1. Oh, that's an error too. So that's not good. Let's try 0. Oh, still an error. This is not good. They won't all be. You can't put a negative in the natural log. That's why we're getting errors right now. You also can't take natural log of 0. But if we try 0.5, oh, finally, got a number. That looks better. All right. So then, what's the next number? Another number you could give me that's closer to 1. 0.25 would not be. 0.75 would be closer. Then I always just like to go to 0.9, and then 0.99, and 0.999. What does it look like this is approaching? Looks like it's getting closer and closer and closer to 1. Right? Okay? Are we all right there? Okay? And then so we do the limit as x approaches 1 from the right of the natural log of x over x minus 1. So let's go delete all these out. What number do you want to start at here? We're coming from the upper number, so numbers higher than 1. 2. All right, let's get closer to 1. 2.5 would be further away from 1. 1.5. Okay, let's get closer. 1.25. 1.1. The numbers you're using here don't matter as long as you're getting closer and closer. 1.01. 1.02. 0, 0, 1. And what does it look like it's approaching? Also 0.9 repeating, which rounds up to 1, right? So these are the same from both sides, so our limit here is 1. Most of the time, if your limit from the left approaches a number, the limit from the right approaches that same number, but not always, so you do want to check. Okay. We don't have time to do these last two, so I'm going to skip those right now. And let's go to the other worksheet, okay, the other notes that you have there. So let me save these. Let's see. All right. All right. Graphically, this is much quicker to do because you're just looking at the graph, so it's much quicker than the ones with the calculator. So just a little notation first, which we've just done the other part, so this shouldn't be so bad. If I have f of x, or f of 3, this is something that we've done for a long time. This is what you get when you plug in x equals 3. Right? So if I ask you to find f of 3 and you've got an equation, you're just going to plug in 3 for your x, and it's whatever y value it gives you. I should say what you get for your y value whenever you plug in x equals 3. For this, we just did this. This is the limit as x approaches 3 from which direction? From the right. If we see a negative behind the 3 instead, that's going to be the limit as x approaches 3 from the left. Okay, so if we see the little plus sign behind the 3, that's from the right. If we see the little minus sign behind the 3, that's from the left. What about if we don't have a plus or a minus sign behind our number? That is the limit from both sides. So this is the limit as x approaches 3 from both sides. And for that to happen, the limit from both sides has to be the same. Right? So, when we've got that terminology down, that's what we need to look at whenever we're asked to find values from the graph. So, let's look at this first graph here. Alright, so, and most of the ones you'll be asked to do from the graph are going to be like piecewise looking sort of crazy functions, not really like an actual graph that you get when you graph a quadratic or something. So, right here, there's something you need to remember. The answers to limits are always y values. Okay, so the answers to a limit are always the y values. We're not reporting the x values here, we're reporting the y values. So, number 1, I've got the limit as x approaches 1 from the right of f of x. So, if I think here, x equals 1 right here, right? So if I'm tracing this graph and I'm coming from the right side, I would trace the graph, trace the graph, trace the graph. Oh, we got a little jump here. As I get closer to 1 from the right, what is the y value that I have, or that I'm approaching here? It is 1. Okay? So the y value that goes there, I'm looking across here and I've got the y value of 1. For number 2, I've got the limit as x approaches 1 and the minus is behind, so that's 1 from the left of f of x. So if I start over here and I trace getting closer and closer and closer to that line where x equals 1, what's the y value that I'm approaching there? 1. Okay, so notice that from the left I approach 1, from the right I approach 1, and I meet right there in the middle, right? Even though I've got a hole in the graph, that open circle tells me I've got a hole in the graph, they meet. So the limit as x approaches 1 of f of x would be 1. At 2, we're going to see it be different. So the next questions after this, we'll see that be different. So if the graph is continuous except for just a hole there, the limit still exists because you're getting closer and closer to 1 from this side and closer and closer to 1 from this side. But what is f of 1? It is not. Because right there at 1, I've got an open circle which tells me that point is not included. What point do I have at, what point is colored in? It is 2. So my f of 1 is 2. So the limit can still exist even if there's a hole in the graph there. Okay? Let's look at these 5 through 8. All of this focuses on the point here at 2. So we're looking at where x equals 2. So that's that vertical line. It's always a vertical line you're approaching here. So from the right, what value do I get, what y value do I get closer and closer and closer to? 3. But from the left, what number do I get closer and closer and closer to? 2, because this is going to stop right here at 2, right? So 2. So what is my limit as x approaches 2? If these two don't match. Nope. It's not the halfway point. There is not one. It does not exist. Because they don't meet. So if you have a jump in a graph, there's a place where the limit does not exist. Because from one side it's one thing and from the other side it's another. So the limit from both sides can exist. What would f of 2 be? Okay, it is 2 because the colored in dot has a y value of 2. Okay, all of these you're always looking at y values that you report. Okay, we're going to do the next graph real quick. We'll probably have to stop that last one. Okay, so if we look at this graph, and some of these are not perfect because they're kind of like between lines. Just estimate if that's the case on the test. I'll try to make them where you don't have to estimate. So f of negative 1. What is our y? We're looking for here at negative 1. I think it's probably 1.5 or 1. It's somewhere between 1 and 2. Any number you give me between 1 and 2 will be fine. I'll try to make it on the test ones that are actually a little bit easier to see. Because right here, we're looking for our colored in dot, which is right here, and the y value that goes with that is right there between 1 and 2. So we're going to call it 1.5. Okay. Number 2 is the limit as x approaches 0 of f of x. And this is from both sides, right? So from the left, we get closer to 2. And from the right, we get closer to 2. Because we're looking at x equals 0 is the y-axis here, right? So if it's continuous, if it just is a straight line, it's just whatever the y-coordinate is there. So we would get 2 for that. Okay. Number 3, the limit as x approaches 2, which 2 is right here, from the right. Negative 3. Okay. What is f of 1? It is 3, because we're looking at the colored in dot, and it has a y-coordinate of 3. What about the limit as x approaches 1? Why not? The limit can still exist even if there's an open circle. Because from the left, what do we get closer to? I'm sorry, that's right. From the right, what do we get closer to? 1. And from the left, what do we get closer to? 1. So it's going to be 1 even though there's a hole in the graph there. Right? Because it's okay if there's a hole as long as it meets on either side of the hole there. What about -1? -1 is right here. What's our limit as x approaches -1? This one does not exist because from the left-hand side, we're getting closer to 0. But from the right-hand side, we've got 3. So this one would be does not exist. So, let's see. Was there an assignment on that I printed you out for 15? No, I need to write down. Okay. All right. So, your assignment will be on page 947. I want you to do 20, 26, 35 through 38. And all of these, use the calculator or Desmos, whichever one you have, to do like we were doing with the numerical ones with that table. Then for the graphical ones, I've got a worksheet